everyone, welcome to lecture 14 of this course. In the previous lecture, we discussed the type assignment theory and the system T lambda. Today we are going to discuss the structure of a term, the construction tree of a term, the subject construction theorem, the structure of a T lambda deduction, the structure of a type and the construction tree of a type. So let us first discuss the deduction in T lambda. We will take a small example. So consider this formula. So let delta be a deduction of a formula with context gamma and term m and type tau. So we call m as a subject of the formula. So in this example, m is lambda f dot lambda x dot fx and tau is this a arrow b arrow a arrow b and the context is empty. So let us see how this deduction proceeds. So the deduction proceeds from this point. So this is the conclusion. So now since here we have lambda f, so that means arrow I men, this rule arrow I men has to be applied. So when arrow I, in order to apply arrow I men, the context should be f has some type. So here f has a arrow b, the type of f is a arrow b and the term here is lambda x dot fx that has type a arrow b. If that be the case, then when we do arrow I men, we get this conclusion. In the same way, now we have lambda x here. So in this step again arrow I men is applicable. So then what the context should be? The context should be what we had before, f has type a arrow b and x has type a and the term is fx has type b. If that be the case, when we apply arrow I men, we get this part. Next we have fx, this is an application, fx has type b. So that means f should have some type and x should have subtype. Now by arrow E rule, it should be f is type a arrow b and x has type a. So that means these parts they match and hence fx has type b. Moreover, if you see the context, here the context is f has type a arrow b and x has type a. So this gamma 1 union, this is gamma 1, you can say this is gamma 1, this is gamma 2. So gamma 1 union gamma 2 is this part. So this is gamma 1 union gamma 2. So this is consistent, hence we can do arrow E and as a result we get fx has type b. Now at this point we see that both these formulas, f has type, in the context f has type a arrow b and we get f has type a arrow b. This is an axiom and similarly x has type a is a context, we get x a, x has type a, this is also an axiom. That means we have arrived at the leaf of this tree. So that means the deduction is complete. So this is the deduction of this, m is lambda f dot lambda x dot fx and tau is this. So we have done the deduction. Now given a deduction delta of tau, in the context tau, m has type tau in T lambda, today we want to understand the similarity of one, the structure of the deduction and the structure of m. That means the structure of this term and the structure of the deduction of m has type tau in the context gamma. Next, we want to understand the structure of the deduction delta and the structure of the deduction of this formula in the context gamma, m has type tau, which is represented in an alternative way. So these are the two things, primarily these are the two things we want to understand in today's discussion. So we will first discuss how to represent a term using a tree, that is which we call as a construction tree. Informally, a construction tree of a term is a tree that depicts how a term is constructed from the subterms of the term. So we give the definition of the construction tree of a term. The node in the tree has two levels, one a subterm and another a position. A position means it is a concatenation of some symbols that we are going to discuss. So integers, say 0, 1, 2 are the symbols. So it is a concatenation of the symbols in some way. So that is called a position. It also includes the empty position. So this definition is taken from Hindley's book. And let m be an arbitrary term. The tree is defined for m as follows. So first we consider when m is of the form just a variable x. So the tree will be a single node tree So here we write this way. So the node of the tree is shown in this way, of the circle with blackened circle. On the left we are going to write the subterm, and on the right we are going to write the position. So here we are going to write epsilon to means an empty position. Next we have this term may be of the form application PQ. So then the construction tree of we have to obtain the construction tree of M given the construction trees of P and Q. So given the trees of P and Q, the tree for M is constructed as follows. So step 1, we concatenate 1 at the left end of each position level in the tree for P. Step 2, we concatenate 2 at the left end of each position level in the tree for Q. Below the two modified trees, place an extra node and label it PQ, this node and the epsilon. So suppose we have the tree for P. Suppose P is just a single node. P is just a single node, then this will be epsilon, and this will also be Q is also, suppose it is a single node. So in the case 1, this is case we are getting from case 1. So then what it is says, the new tree will be, this is the new node. So this is the new node that we have placed below these two trees. So we put these two links we add and we say PQ, and the label is position label is epsilon. So now what it says, concatenate 1 at the left end of each position level in the tree for P. So here we have epsilon. So epsilon left end I will put 1, and here epsilon left end I will put 2. Now any position P epsilon is the same as P. So that means 2 epsilon, 1 epsilon is equal to 1. So we have got 1 here. Similarly, we have got 2 here. Now instead of this simple thing like one element, one node tree, that could be a tree. It is not the trivial tree, but it could have many nodes, multiple nodes. So that means that each node, what it says, that for all the position levels that are there for the nodes, we will concatenate 1 at the left end of each position level. So that means if suppose there was a node here, so that node level was this way, there were two positions. So on the left hand we are going to add 1 here. Similarly here it was like this, so we will go add here 2. This is the idea of constructing the tree for PQ. Now we have an abstraction like lambda x dot P. That means we are given the tree of P, we are trying to construct the tree for lambda x dot P. Now again as before, so this was the tree for P. So this is the new node that we have obtained. So we are placing one extra node and labeling it lambda x dot P epsilon, and here we are going to concatenate 0 at the left end of each position level in the tree for P. That means if there was any other node here, so then this position level was like this, so we are going to place 0 at the left end of each position level. So this completes the definition of the construction tree of a term. So now we take a very simple example and work out the construction of the tree as per this definition. So this term is lambda f dot lambda x dot fx. So there are 2 abstractions and 1 application. So we start. So here, so we need to so the idea about this is at each node we are writing 2 things. One is a subterm and another is a position. Now subterm of a term M, if M is a term, subterms will be, M will be a subterm of M. M will be a subterm of M. Now we can consider different cases like say if it is an atomic like X, then subterm will be X. So we can write, so we can say subterms of M. So X is just a variable, then we can say X is a subterm. Now if you have a term like lambda x dot P, then lambda x dot P is a subterm as well as all the subterms of P, And if we have a term like PQ, then it will be subterms of P union with subterms of Q. So these are with the subterms. All the subterms there, they will be placed as every node in the tree will be labeled with one subterm. So here let us see what are the subterms here in this term. So if we see this carefully, So we have lambda f, lambda x, fx. So this is one subterm. Another subterm is lambda x dot fx, because it contains this, so this will be another subterm. Now this contains fx, so this is another subterm. Now fx has again application pq, so f and x. Nothing else will be a subterm. So there are how many subterms are there? 1, 2, 3, 4, 5. So there are 5 subterms in this. So the tree will contain 5 nodes, and each of them will be labeled by one such subterm. So that is the idea. So the idea of constructing this tree is from these simple subterms. That means here f and x. So we start with f and x. So that is the atomic case, m is equal to x. So that means individual we have labeled, f will be, it will be a node, single node tree with the level subterm is f and your position is empty position. Similarly, subterm is x and empty position is epsilon. So that is step 1. Next we are doing application, that is, it is of the form, m is of the form pq. So what it says, we concatenate 1 on the left end of each position level of p and concatenate 2 on the left end of each position level in q. So that means here earlier it was epsilon, so we placed 1 here, here it was epsilon, we placed 2 here, 1 epsilon is 1, 2 epsilon is 2. So we have got this. This is the new node that we have obtained, and that is labeled as epsilon. Next we have the abstraction, that means lambda x dot fx. So that means this was our original tree. Now lambda x dot fx will be the, this is the new node and it will be labeled with epsilon. And what it says, this 0 will be the label of this part, fx will be labeled, that means 0 we place here and 0 will concatenate at the left end of each position level. So that means we had 1, we had 2, 0 was placed here, 0 was placed here, we got this. So this is the tree that we have obtained from lambda x dot fx. Next we have to do lambda f dot lambda x dot fx. So we have to add one more here, one more such node we have to add here. So let us see how we get. So now up to this we have seen how to construct the tree up to this part. Now we have added lambda f dot lambda x dot fx. This will be epsilon. So again the 0 will be concatenated on the left end of each subtree. So here this 0 is added, this 0 is added, this 0 is added. Now this is 0. So we have got this entire tree. So let us see how many nodes are there. 1, 2, 3, 4, 5. So there are 5 subterms. So we have 5 nodes, each of them labeled as this way. Recall that we were trying to understand the relationship between the structure of a deduction in TL lambda. That means if I have a term like, for the context is empty, m has type tau, and the deduction of this and the tree structure of this term m. So for this example that we have been working with, so this is our m and this is the tau, and we have seen the deduction of this m has type tau in TL lambda. Now here what we do, the subject of this formula is, in this the subject is m is the subject of the formula. So for each formula we are going to keep this subject, that means we are erasing the context and the type. So here for example, here context we will erase, type we are going to erase, so only thing that remains is this x, that is the subject. Similarly we are going to keep this f here, and likewise for each formula we are going to keep only this part, and rest we are going to erase. If we do like this, after this the transform tree will look like this. So it has only the subterms, see fx, fx, lambda x dot fx and lambda f lambda x dot fx. Now we can see the relationship between the structure of this deduction in TL lambda and the construction tree of m. So right hand side, this is the construction tree of m, this is the construction tree, and this is the delta that we have obtained. That means what we have done, from the deduction we have kept only the subject and erased the context and the type from each formula. And in this construction tree we have omitted the position labels. So then what we have obtained, these are two structures, they are depicted. One is a natural way we do it, is a horizontal line, that means this is called the conclusion and this is called the premise. So this is the structure of a deduction, And here instead of doing that, we put nodes in a tree as if these are the nodes of the tree and then the links or the edges of the tree. So these two structures we can see they are similar, just represented in a different way. So this is the first thing we started with, and this is the through the example we got some informal understanding. So here just to note that this deduction was constructed bottom up. We started from the conclusion and we obtained this tree. Whereas here the construction tree was obtained from simple subterms. That means we started from this xf and we constructed it and we obtained this tree as per the definition of the tree. Now let us consider another example of the construction tree of a term. Now here this term is lambda x dot lambda y dot lambda z, written in a shorthand y x z. So this will be the different steps that we are going to show. That means first we are going to give the construction tree for the subterm xz, then we are going to obtain the tree for the subterm yxz, then lambda z dot yxz, then lambda y dot lambda z dot yxz, and then finally the entire term. So this is what we are going to show. So we have omitted the steps that x and z were created with the single node tree. We have got an understanding of that, and now we can do this x, y, x, z step. So 1 will be placed on the left hand, 2 will be placed on the left hand of the z corresponding to the node for z, and like this we obtain xz. Now similarly we will obtain the tree for yxz. So yxz, this subterm, the position level will be epsilon. Now for the subtree, the left subtree, we will place 1 at the left end and we have to place 2 at the left end of each position level, 2 at the left end of each position levels. So now you see what if you recall the definition, it says the modified trees. The modified trees means now this is one tree, this is one tree. So this tree's position levels are now changed. The tree is not changed in any way. It is the position levels that are changed. So it was earlier 1 and 2, and now this position level has become 2 1 and 2 2. This is what we mean by modification. Modified tree means their position levels have been modified. So now the yxz part, this part of the term, we have constructed the tree. Next we have to add these abstractions. So we will add one by one. So 3 abstractions means 3 steps we have to add. So we will again add this part. So that means here now 0 will be contained at the left end. So the 0 has been added to all the nodes in the tree, both the left branch and the right branch. And in the same way we are going to add lambda y and lambda x. So when we add lambda y when we have added, again another 0 we have seen it is added, another 0 is added, and then finally when we add this lambda x, another 0 we have added. This is the another 0. So this is how the trees get modified, in the sense that their position levels get changed. So let us see the position level of a subterm. So if it is of length n, it means that the subterm is at a depth n of the tree. So for example, here this position level length is 5, and let us see the depth. This is depth 1, this is depth 2, depth 3, depth 4 and depth 5. So the position level is telling, it is giving us some information as to where this subterm is located, or what is the position of the subterm in that term. That information is being provided by this position level. Now again we want to discuss the similarity with the deduction structure of the deduction of this formula in T lambda and the construction tree. So this is the deduction of this formula in T lambda, and the subjects are shown in red. That means when in the transform tree we are only going to keep these subjects and erase the context and the types. So these are the subjects at different points. So here it is x, it is z, here it is xz, it is y, here it is yxz, here it is the lambda z dot yxz, lambda y dot lambda z dot yxz, and it is lambda x dot lambda y dot lambda z yxz. So then the transform deduction tree will look like this. We only have the subterms. It is the x, z and so on. So now we can, when we place these two things together side by side, so here again we have in the construction tree we have omitted the position levels, and here this was the transform tree from the obtained from the deduction of m has type tau in the context gamma. So we see that they are, it is instead of horizontal lines, again we see we have nodes of the tree and we have links or the edges of the tree. So they are just represented in a different way, but their structures are same. So once again through the second example also we have found that the term construction tree of a term, the structure of the construction tree of a term, when we just keep the subterms and omit the position levels, this structure is the same as the deduction of m has type tau in the context gamma in T lambda, where we have kept only the subjects in the deduction, omitting the context and the type. Just that we are not doing horizontal lines the conventional way of writing deduction. Instead of that, we are placing it in a tree like structure where position levels are added. So this is the, so now that we have got an informal understanding about the structures, two structures, one is the that of a tree, construction tree of a term m, and the structure of a deduction of the m, that is the formula gamma in the context gamma, m has type tau in T lambda. These two structures are same. Now that we have got an understanding, an informal understanding about the similarities of the structures of deductions in T lambda and the construction tree of a term, now let us see the meanings of position levels. So suppose we are given a construction tree of a term and it looks like this. So we are taking as if this part only and it is up to this. So position levels, we see the symbols are 0, 1 and 2. So on the right hand side of these nodes we are writing the position levels. So the significance of this 2 means when if I have a position symbol written in this way, so there are four symbols. So the rightmost symbol, let us concentrate only on the rightmost symbol. If the rightmost symbol entry is 2, this means it is an argument. If the rightmost symbol entry is 1, it means it is a function. And if the rightmost symbol entry is 0, it means it is a body of function. So this is the meaning of the symbols 0, 1 and 2. That means the position symbols is not just an arbitrary concatenation of these symbols 0, 1, 2. It has some meaning, and looking at it we can interpret this term very easily. So for example, we know this will be the root of this. Here we are going to write the term m, entire term will be written, and by the construction here we are going to write epsilon. And now because it was an abstraction, because this link means it is an abstraction, that means their right hand position will be 0. It is by the construction it is a body of the function, because here this m means the lambda x sort of a thing dot something came, and then that something is labeled here, and this is the position level will be 0. Now going to upwards, this one is a function. So that means here whatever we do, like right hand side will be, rightmost symbol will be 1, and here the rightmost symbol will be 2, because this is function, this is argument. Now we can say what else will be there in 1, 2, because we know by the construction that when this abstraction was added, this 0 was concatenated at the left end of each position level. So that means this will be 0 here, this will be 0 here. So this is 0, 1, this is 0, 2. Now moving upwards, then here again rightmost will be 2 and rightmost will be 1. What will be the other things? It will be 0, 2 here. This will be 0, 2 here. So here now if we see this position level is of length 3. That means it has a depth 3, 1, 2, 3. So that means when f is applied to x, that means they are at the same depth. F is a function and x is an argument. Their position levels will differ only at the last point. That means at the rightmost position it will differ. The function will be 1, argument will be 2. other things, other symbols concatenated before this, they are same. And whatever symbols that appeared before this, that is coming here in the body. So this is, we can say this part will come here. Again this part, this 0 part you see here, it is common. 0 is common, this part. It differs only, it is now depth 2, so the length is 2. So here it is differing only 0. This 0 is coming here, this will be 0. Now here there is again epsilon, 0, we can say 0 epsilon. Now this epsilon is coming here and this is of depth 0. Thus we have got a meaning of these terms, these positions, meaning of the positions. And if you have, when you are constructing this, obtaining a construction tree of a term, when you are writing the positions, you can well verify whether your position labels are correct or not. You cannot put arbitrarily something like, you cannot put it here 101, you cannot put it 102. This is not correct, and you can easily verify it. It is obtained by the construction or the definition of the construction tree. So this is a nice property of the position labels. So now we are in a position to discuss the subject construction theorem. The subject construction theorem is taken from Hindley's book. It gives the structural relationship between the deduction of the formula M has type tau in the context gamma and the construction tree for M. As we have seen, these two structures are same. As we have discussed, we have erased certain things here, we have erased certain things there, and we have got the same structure. This theorem provides the deductions to terms correspondence. That means the given lambda term M, if we obtain the construction tree of M, that is the same as the deduction of M for the context gamma when this term has type tau in the system T lambda. This is what we have obtained. And then the property, we can say that the tree structure of the deduction of this formula in T lambda and the tree structure of M are same. We have seen through these two examples. And this property is important since it does not hold in many complex type theories. It is true in T lambda, but it need not be true in other complex type theories. That is the idea of subject construction theorem. Subject construction, simply put, given lambda term M, that in the formula gamma, context is gamma, M has type tau, the subject is M, and construction is the construction tree of for M. So that means when we are taking out the subject part from the deduction of this formula in T lambda and we are looking at the construction tree for M, these two things are same. That is what this subject construction theorem is telling us. Now we are going to study the structure of a T lambda deduction. We have seen that a T lambda deduction is represented in a conventional manner with premise, then premise horizontal line, and then a conclusion. This is how the inference rules are written, and we have seen different examples. Another way of giving the deduction is via a tree-like structure. So this tree-like structure that we are going to do, it is very much similar to the way we have defined the construction tree of a term. So a T lambda deduction is a label tree where a node has two labels. One is a T lambda formula and another is a position. So again we are taking the definition from Hindley's book. So earlier it was a subterm and a position label. Here it will be a T lambda formula and a position label. Position labels will be defined in a very similar manner. Instead of now having subterms, we are going to have T lambda formula. So consider first the atomic deduction. That means it is an axiom. So it will be a single node tree where the node is, this is the node of the tree, position is empty position, and this is the axiom, this is the formula. Now when we want to say PQ sort of a thing, that means application. So that means if delta 1, delta 2 are deductions whose bottom nodes are labeled as this formula, that means we have labeled it by this is the formula and this is the node of the tree which has this labeled. The labeling is, this is the formula and this is the empty position. Similarly, this is the formula and this is the empty position. And gamma 1 union gamma 2 is consistent. Then a new deduction delta 1, delta 2 is constructed as follows. So, we concatenate 1 at the left end of each position level in delta 1, then we concatenate 2 at the left end of each position level in delta 2, and below the two modified deductions place an extra node where the context will be gamma 1 union gamma 2 and the term will be pq and the type is tau and the position is an empty position. So, it is like this. Thus, this is the modified delta 1, modified because of the concatenating 1 onto the left end of each position level. So, all the nodes that are there here, all their position labels will be modified. So, this is our formula here and this is gamma 2, this is the formula with respect to q. Again q delta 2, this node in delta 2 will be modified. So, then finally, we are going to get this label gamma 1 union gamma 2 pq tau and we are going to get empty position. So, now we have to consider the case for abstraction. Now, if delta 1 is a deduction whose bottom node is labeled as gamma, the formula gamma in the context is gamma and p has type tau and the empty position is the label of the position label is epsilon and gamma is consistent with x has type sigma, then a new deduction lambda x dot delta 1 is constructed as follows. So, we concatenate 0 at the left end of each position level in delta 1 and below the modified deduction place an extra node that is gamma minus x, that means from gamma we are excluding x and then we are doing lambda x dot p and that will be that has type sigma tau and the position is empty. So, this is shown in this way that this is the new node that we have placed and the label is this. This was the earlier node that was there, bottom node of the deduction delta 1 and if I have a node here, the position label left end I will put the 0 here and that is the idea of representing the structure of T lambda as a tree. So, consider we will now illustrate this idea through this example. So, earlier we have seen the deduction, this was the deduction in T lambda. Here what we have done for each formula we have kept one, we have named it as delta 1. Delta 1 means this one, this part. Similarly, delta 2 means this entire. So, here we are doing different steps arrow E and arrow I and so on. So, we have delta 1 to delta 8. So, we have instead of writing this entire term that will look, it will be very difficult to read and it will be. So, we will be writing instead of this entire formula, we are going to write the delta 1 instead in the tree that we are going to construct. So, now as before we will be moving in steps. So, first this application part we are doing. So, delta 1 and delta 2 we are considering. So, we get this delta 4, that means then again there is an application. So, delta 3 and delta 4 we obtain delta 5. Again you see the position labels have changed, this 2 is added all throughout. Now comes abstraction. So, that means 0 will be placed everywhere at the left end. Again there is a lambda. So, again another 0 is added at the left end and then again there is a last another one more lambda. So, again this part is added. So, this is the tree structure representation of T lambda deduction. So, now putting these two things together, here we see the similarities of one, this was our T lambda deduction where we have horizontal lines and here it is the nodes of the tree and the link or the edges of the tree. So, if we remove the position labels, they will be the same, these two structures will be same again. So, now what we have now? So, in the system T lambda, deductions can be represented in either way. One is this way that we have done, the earlier way that we are used to, and now if you want to include the position levels as well, we can put this. Both these things, the structure of both these two ways of writing or two ways of conveying this deduction, they are same. Okay, now we are going to discuss the structure of a type. We have seen the structure of a T lambda deduction, we have seen the structure of a term M, and now we have to discuss the structure of a type, that is the construction tree of a type. It is similar to the way we have done the construction tree of a term or a construction tree of a deduction. So, now we have to consider two cases, because here there is no this application is there, but abstraction nothing like abstraction here. So we have an atomic type, say A, so which we are going to represent as a single node tree. So the node is this one and the empty position, and this is the term or the type that we are going to do. Now we have only the other case, that is arrow type because the formulas are only composite A arrow B sort of a structure. So sigma arrow rho we have to consider. So given the trees of sigma and rho, the tree of tau is obtained in as follows. So we will concatenate 1 at the left end of each position level in the tree for sigma, and we concatenate 2 at the left end of each position level in the tree for rho. And below the two modified trees, place an extra node and label it sigma arrow rho, and empty position is epsilon. So this is how the tree will look like. So we are now quite familiar with this sort of structures. Only thing is now these terms or deductions we are replacing with types. So here it will be sigma arrow rho, and it is sigma, it is this. So you can think of this thing to make it a little analog with what we have discussed. It is this application. Sigma arrow rho, you think of it as PQ, P applied to Q. So whatever we do it there, we are exactly doing this here. So we take a simple example like A arrow, B arrow, A arrow, B. Remember that if we had not written this parenthesis, it would have still meant this one, because arrow is right associative and we have to place this. However, this one we cannot throw away. This one we cannot throw away. We have to keep A arrow, B. So the understanding of this type is, it is having one, there are two arguments. One is a function type, another is an atomic type, and the return type is also an atomic type. This is the function type, this is the atomic type, and this is the return type. So for doing these constructions, we are always going to write in a form like sigma arrow rho. This constructions we are always going to have it in this. So we are going to place brackets. That is why we have placed the brackets there or the parenthesis there. So I will show that A arrow B, because both the parts of sigma and rho, they are same A arrow B. So if I do one, the rest will be identical, and then proceed to the construction of sigma arrow rho. So A arrow B, this is that A will be, originally it was a single node, so epsilon 1 was concatenated on the left hand, 2 was concatenated on the left hand, so we get these two nodes, and then A arrow B epsilon is the node placed below these two nodes. Now this tree that we have obtained, it was we did some work. So we did some work here. So what we had here earlier we had epsilon. This is 1 and this is 2. Now this is the new node that we have placed beneath these two. So the rule says on the left branch you concatenate 1 to the left end of each position level. That means here 1 came, here 1 came, here 1 came, and on the right you concatenate 2 on the left branch. So here 2 was placed, 2 was placed here, 2 was placed. So we got this. So this is the position levels. Again you see this length is 2. That means from the root it is having a depth 2. This is position level is 1, length 1. So it is from depth 1. They are differing only at these two, because this we can think as PQ. So this will be 1, this will be 2. Rest are same. This is 1, this is 2. So we can verify and find that this is correct. Now we take a little bit more complicated, in the sense that we have some more involved formula here. So it is again written A arrow, B arrow. So sigma arrow rho structure. So again we do part wise, and then we combine together and we get the construction tree of the type, the entirety. So first, as before, we got A arrow B part we have shown here. This is quite straightforward. Now B arrow C is again similar to the other one. A arrow C would be like this. It is in the lines of the previous two. Now we do B arrow, C arrow, A arrow, C. Now as before, whatever we did for A arrow, B arrow, A arrow, B is the same thing. So this will be the same structure. It will be the same structure. We can verify the position levels are correct. This is A arrow C, this is B arrow C, this is this. So we have a node here. A arrow C means the tree grows by 1, and moment we bought another arrow, the tree grows by 1. As if we are doing this, although the tree is written in a natural tree. So this is the depiction of the trees that we have done so far is a natural tree, not the trees that we are acquainted with in computer science, where the root is at the top and the leaves are at the bottom. Here the root is at the bottom and the leaves are at the top. But the tree grows in a quite different way. We start with the leaves as if the tree is growing this way. So when you do an application sort of a thing, we have the edges and we put this. Application in the sense here it will be A or B. So we got here. Likewise we got here. Again we are doing application. That means this arrow is coming. So when I say application, so I am making an analogy with my earlier definitions, and the arrow corresponds to application. So we have got this part. And we will remember this analogy also. We will see later on whether how this analogy holds later on. When we are going to have later discussions, we will see the importance of this analogy as well. So finally, the entire tree looks like this. So here, for example, if I take this depth, so here this is my A R O B part, and this is the this part B R O C R O A R C is this. So here we see we want to verify. So this is the AROC, this is BROC, this is at depth 3. So that means 3 levels are 3. They will differ only at the last point 1, 2, 2, 2 same. This comes 2, 2 will be here, 2 will be coming here, epsilon coming here. Same thing here 2, 1, it is 2, 1, 2, 1 here, 1, 2 differing. They are differing here at these 2 points. So this is epsilon, this is epsilon. So differ at these points. So this is epsilon. This is 1, 2, this is 1, 2. Now you see when you are at the different branches of the tree, if we want to have a better understanding, so this is one part of this tree. Now if we want to correlate these two terms, these two nodes which is across, this is one part of the tree, this is another part of the tree, subtree, you can say right subtree, left subtree, and if you take the corresponding nodes, you see their length of the position elements must be same. That means they are BROC and AROC they correspond, and then that correspond means that is PQ structure we are doing, PQ. So PQ we get here PQ. So their position levels must be same. Here whenever they are at the same level, their position levels are same. That means this is PQ structure. Here PQ structure, here PQ structure, here these two are at the same level. So these two correspond, so their position levels are of the same length. Here they are same length. So this is the relationship of the tree. So once when you are initially doing it, if you may find it hard, but you can verify it very easily whether your position levels are correct or not. It is very easy to do. The tree structure, although here the depth of the tree is 3, and the more complex the formulas would be. So in this part also more complex, the tree structure will be rather complex. However, it is easy to read and easy to verify the position levels as well. And assigning the position level also by the construction is pretty straightforward. So thus we can summarize the discussion. We discussed the structure of a term, and for this we introduced a tree which is called the construction tree of a term. We have give the definition of the construction tree. Then the idea about this correlation with deductions and terms is formalized in the theorem called the subject construction theorem. And then we gave an alternative way of writing or showing deductions in TL lambda in the tree structure that we have discussed. And then the structure of a type also was considered, and again the tree structure is a construction tree of a type which is similar to the construction tree of a term. So with this we conclude today's discussion, and the reference is that Hindley's book, A Basic Simple Type Theory, and please refer to chapters 2 and 9. So with this we conclude today's talk, and thank you for your kind attention.